Welcome back to digital filter design. Today we'll see the second method of digital filter design. Digital filter design using bilinear transformation. So this is a given problem statement for h of e power j omega with respect to the frequency and h of e power j omega for this value, the range of frequency. When you are plotting this value in your response curve, x-axis is nothing but your frequency and y-axis is nothing but your gain, that is magnitude of h of e power j omega. When you are plotting it, the curve will look like a low pass filter. Since 0.8, the pass band frequency range is 0.2 pi. For the stop band range, the value is 0.65. When you are joining all the points, it look like a low pass filter. What are the steps to be followed? First, we have to calculate the order n. With respect to the order, we have to calculate the normalized Hn of s. Then we have to calculate the cutoff frequency omega c. Then we have to calculate Hn of s, where we have to replace the value of s is s by omega c. Then unnormalized h of s is equal to replace s as 2 by t 1 minus z inverse divided by 1 plus z inverse. So this formula is we are going to use for bilinear transformation. First we'll see how to calculate this n. N is equal to log of 10 power minus k1 by 10 minus 1 divided by log of 10 power minus k2 by 10 minus 1, the entire division by 2 log of omega p by omega s. In order to calculate all those values, we should know what is k1, k2, omega s and omega p. Let's see the formula. So the given in terms of digital, we have to convert the digital value to the analog frequency, analog gain, where the value of k formula is 20 log of e power j omega. Similarly, k2 is 20 log of h of e power j omega at stop band as well as for pass band. When you are substituting the value for pass band, the k remains as 1.94, which is in terms of gain. Then we have to calculate k2, it is 13.98 dB. While substituting the value of 0.8 as well as 0.2, we'll get this answer. Then we have to calculate the frequency for analog. Since we know all the formula in terms of analog, we have to convert. For bilinear transformation, the formula for omega p is 2 by t tan of omega p by 2. Omega s is equal to 2 by t tan of omega s by 2. So what is t? If the problem, if they given the t value, we have to substitute. If they didn't specify, we have to write it is 1 seconds. When you are substituting the value of omega p and omega s, the value of omega p is 0.65 radian per second. Then we are calculating for stop band frequency. The answer is 2.75 radian per second. So now we got both the values of k1, k2, omega s as well as omega p. When you are substituting in the order n, the answer is approximately equal to 1.7. When you are going to round off, the answer is equal to 2. Now we got the n value. After calculating the n value, we should specify for order n what is your Hn of s. We already know the formula for order n2. It is 1 by s square root 2s plus 1. Then we have to calculate the cutoff frequency omega c. The formula to find omega c is with respect to pass band omega p divided by 10 to the power of minus k1 by 10 minus 1 the whole power of 1 by 2n. We know what is omega p, already we have calculated. We know what is k1, that also we have calculated, it is 1.94. n order we know it is 2. After substituting all the value, the answer for omega c is 0.75 radian per second. So now we got the second solution for cutoff frequency. Then we'll move on to finding the normalized Hn of s. So we know the formula for Hn of s, that is 1 by s square root 2s plus 1. There we have to replace the value of s. S is equal to s by omega c. When you are replacing, the formula will remains like this. We know the value of omega c. Omega c is nothing but 0.75. After writing, the solution is 0.5625 divided by s square plus 1.065s plus 0.5625. So this is a solution of h of s under normalized condition. After calculating h of s, we have to calculate in terms of z, h of z, where we have to replace the value of s as 2 2 by t, 1 minus z inverse by 1 plus z inverse. So h of s is 0.5625 divided by s square plus 1.065s plus 0.5625. We are replacing the value of s as 2 by t, 1 minus z inverse divided by 1 plus z inverse. As we know, t is equal to 1. After taking a LCM of this denominator term, the value of h of z is 0.5625 z power minus 2, 1.12 z power minus 1, whole division of 2.4425 z power minus 2 minus 6.875 z power minus 1 plus 6.68. So this is our transfer function for our given problem in terms of digital filter. So this h of z transfer function is have to implemented in direct form 1 or by using direct form 2. So realization of digital filter is very important. So after finding h of z, we have to realize either by using direct form 1 or direct form 2.
Welcome to the topic digital finite impulse response filter. So finite impulse response filter, in short we call that as FIR filter. So how to design FIR filter and why these FIR filter designs are more popular than IIR filter design, we are going to see in this session. So when we are coming to FIR filter, we already have seen what is filter, why filtering is required. We have seen the design of IIR filters using various methods. Now we are going to see FIR filter. So these FIR filters, we are going to see here the form of FIR filter, what is the impulse response. So why it is called as finite impulse response filter. So the impulse response, you can see here the impulse response of the filter is of finite duration. It is not like IIR filter, where in case of IIR filter the impulse response is of infinite duration, and here it is of finite duration. So that means it is from 0 to n minus 1. We know the impulse response is of finite length, and also this FIR filters are recursive system. So why recursive system? Because the FIR filter transfer function already we have seen, that is equal to k is from 0 to n bk z power minus k. So here the output of FIR filter, it depends only on the present input as well as past inputs, but not on past output, and because of that the FIR filters are non-recursive. There is no feedback system here, and that's why they are stable. So this comes under the advantages of FIR filter. So the first advantage is they are stable, always they are stable, whereas in case of IIR filter they are unstable filter. And one more advantage of FIR filter is they are linear phase. So what is linear phase, that I will be talking later. So because of this feature, that linear phase, we will be reducing the number of computation when we go for filter design. We will be using the property of linear phase, and we will be making simplification in our design procedure. And also this, we have excellent methodologies available for design of FIR filters. So these are the advantages of FIR filter. Now coming to the disadvantage, the computations in FIR filter, it is more. So compared to IIR filter, FIR filter, we need to do lot of computation, but those computations are easy. So in terms of the time required, it is more, and also the memory requirement more, and also to implement the filter we need more components. So the disadvantages, we can write that as requires more components, requires more memory, and more computation. So these are the disadvantages of FIR filter. Now we will see first what are the properties of FIR filter, because once we know the properties of FIR filter, then only we can go for exact design procedure. So what are the properties of FIR filter? So we saw that in IIR filter, how the IIR filters are characterized. So always we are characterizing the filter in terms of their either by their impulse response or by their magnitude response. So in case of FIR filter, the magnitude response of FIR filter is given in the form of C into e power minus j omega alpha, where omega is nothing but the frequency which lies in the range from minus pi to pi, and the value of this magnitude response equal to 0 other than the frequency range from minus pi to pi. What is this alpha? This alpha is called as center of symmetry. So this alpha is called as center of symmetry, omega is nothing but the frequency, and this h of e power j omega is magnitude response. So in case of FIR filter, the magnitude response has this form. So what are the properties of FIR filter? So we will list the properties of FIR filter so that it will be easy for us to design the filter. So the first property of FIR filter, it is linear phase. So FIR filters have linear phase. Why they are having linear phase? We will see that this given h of e power j omega, that is nothing but the magnitude response, is complex in nature because it is a function of omega here, e power j omega, it is a complex function, and we know that any complex function can be written in terms of its magnitude as well as phase. So when we write this h of e power j omega, its magnitude and also its phase, which is equal to C into e power minus j omega alpha according to this equation, where this h of e power j omega, the magnitude, the modulus of this is equal to C, which is nothing but constant, and this theta of omega, nothing but the angle or the phase, which is equal to, it is matching with minus omega into alpha. You can see that here the phase of the FIR filter, this is the magnitude, this is the magnitude, and this is the phase. So the phase of FIR filter, which is equal to minus omega into alpha. Alpha is center of symmetry, which is also one constant value. So if we see here this theta of omega, the phase which is proportional to omega, that means this value of the phase is dependent on the value of omega. So as the omega value, this is negative relationship, so as the omega value increases, the phase is decreasing function, and if we try to plot it here in this axis as omega and this as theta of omega, we will be getting the function like that. You can see that it's a linear relationship, there is no non-linearity involved in this equation. So from this we can say that the FIR filter has linear phase. This is the first property of FIR filter. So coming to the property, second property of FIR filter. So the FIR filters, we know that it's linear phase. We have already proved it in the property number 1. And according to this second property, if the FIR filters are linear phase and if it is symmetrical impulse response, then its impulse response h of n is equal to h of n minus 1 minus n, where this capital is N is nothing but the order of the filter, and you can see that here using this property we can reduce the number of computation. So since h of n is equal to h of n minus 1 minus n, suppose if we have to design a filter of length, say it is equal to 8, then if we find out only the coefficients h of n, 4 coefficients of h of n, it is enough, because the remaining 4 coefficients we can find out using this property. Similarly, if the FIR filters are antisymmetrical FIR filters, then its impulse response has the property which is equal to h of n equal to minus of h of n minus 1 minus n. So using these two property, based on the nature of the FIR filter, either it is symmetrical or antisymmetrical, we can reduce the number of computation. So designing filter, before itself I already have said, when we are going for designing the filter, we are finding the coefficients of h of n. So when we find out the coefficients of h of n based on the length of the filter, in case of FIR filter, if we find out the half of the filter coefficients, it is enough to find out or to design the filter, because the remaining half coefficients we can find out using the property 2. Next property is the property 3, where it is the output of FIR filter is scaled and delayed version of the input sequence. So already we know that the FIR filter has the form, it is equal to C into e power minus j omega alpha. This is nothing but the magnitude response. We already know that the magnitude response is nothing but the ratio of its output as well as its input Fourier transform. So if I write this DTFT, so either you can take this FIR filter where you can take the DTFT of x of n, which is x of e power j omega, y of n, which is y of e power j omega, and if you take the ratio, that is become the magnitude response. So I have written this magnitude response in terms of output as well as input, which is equal to C. C is nothing but some constant, the magnitude, and e power minus j omega alpha, which is nothing but the phase of the filter. Now just by performing the cross multiplication, we can write this as y of e power j omega, which is equal to C into e power minus j omega alpha into x of e power j omega. Now let us give this equation as number 1, this equation as number 2. Now if we take the inverse discrete time Fourier transform of this expression 2, so by taking the inverse discrete time Fourier transform, we will be getting that as y of n. So what is the relationship between this y of n and y of e power j omega? They are the DTFT pair. So we will be getting y of n. You see that in the right hand side you have C, which is a constant which is not having any effect, so we can write as it is when we take the inverse discrete time Fourier transform. But when we apply the discrete time Fourier transform on this terms, that is x of e power j omega, which is multiplied by e power minus j omega alpha, the answer will be x of n minus alpha, because this alpha is nothing but the amount of shift which is given in terms of e power minus j omega. So here you can see that now this is the output, y of n, which is the output of FIR filter, and the input is x of n. So what is the relation we got here in this expression 3? The output of FIR filter is scaled. Why it is scaled? Because you can see that the C is the constant, which is the magnitude, which is a scaling factor here, and x of n is input. What is x of n minus alpha? That is nothing but the delayed version. So the output of FIR filter is scaled and delayed version of its input. So these are few properties of FIR filter. We'll be using it when we are going for detailed design of the filter. So we have seen the FIR filter properties. Now we are going to see the design procedure for FIR filter. So for designing the FIR filters, we have various methods available. So I have written the methods here. So these are the methods, some of the methods available for designing the FIR filter. So it is given here as Fourier series method. Then we have frequency sampling method, we have window method, and we have optimal filter design method. So out of these 4 methods I have listed there, so that third method, that is window method, is very simple to design FIR filter compared to any other technique. Other methods will take more computation time as well as complex design methodologies. Compared to that, only the window method has greater advantage of simplified design. So we are going for window method because it will be as a for starting the design, this will be very easy, and once we understand the window method, we can go for learning the other method by referring the reference books which will be given to you. So next we are going to see the FIR filter design steps using window method. So what are the steps? So for designing the filter, always we have seen that in case of even IAR filter, the specification will be given. So from the given specification, we have to first read the specification, understand what is the filter. So we have to find out what is the, from the given, specification, we have to find out what is the desired frequency response. That means we know that the filters may be of type low pass, high pass, band pass or band stop. So once we read the specification properly and if we try to write its magnitude response, the desired magnitude response, we will be able to find out the given specification is for which type of filter. So that is denoted by HD of e power j omega, where D is nothing but the desired. D stands for desired frequency response. If we want, we can give the other name also. So next is we have to take the second step. We have to take the inverse discrete time Fourier transform of this desired frequency response to get HD of n. This is in frequency domain, this is in time domain. So this HD of n, what we are going to find after taking the inverse discrete time Fourier transform, this is of infinite duration. So that means here from minus infinity to plus infinity, the length is infinite. So we do not want the filter to be infinite, we want FIR filter design, and hence we have to reduce this HD of n, the length, to a finite length. And how this can be done? This can be easily implemented using the step number 3, where we have to find this h of n by multiplying this desired HD of n along with the window function. So window function is nothing but the function which is going to give you the finite duration impulse response instead of infinite. So you see that before applying the window, the infinite impulse response, the impulse response length was infinite duration. But how we are making it finite? By multiplying this HD of n with window function. This window is specified for period, that is omega of n, and if you take in terms of time domain, with respect to n, the window function is already defined, predefined window function, and hence we will be making this infinite duration length into finite duration length, where this our now h of n will have the length from 0 to n minus 1. So this h of n will be of length, this n will be of length, this n is of length 0 to n minus 1, and hence the infinite filter becomes finite filter. So now next step, what is the next step? We are going to design the digital filter. So always when we are going to design the digital filter, we have to find out the transfer function of the digital filter. So h of z. So how we are able to find? By taking the z transform of this h of n. Once you take the z transform, you will be getting h of z. So once we get h of z, that becomes digital filter design, which is now completed. But we cannot say that filter design is completed unless and until we have used the suitable form for realizing the filter. So we need to realize the filter. To find out how many components are required to implement the filter in real time, we have to go for implementation. We have already seen the design steps for FIR filter design using window method. So there in the first step, we have seen that we have to first identify what is the specification given, and then we have to draw the specification in terms of either low pass or high pass, band pass or band stop. So based on the specification, we are going to find out the filter belongs to which category. So here I have given for low pass, high pass, band pass and band stop the characteristics drawn here, the magnitude response, where the x-axis is omega, y-axis is the frequency response HD of e power j omega. So the filter specification may be given for linear filter, or maybe it can be given for ideal filter also. So in that case, we should know both the characteristics, what should be the value. So I have written both the specification for ideal filter as well as for linear filter. So if the filter is given ideal filter, we have to design, but we cannot realize the ideal filter because the ideal filters are practically not realizable. So in that case, at the last design step, we need to convert the ideal filter into linear phase filter, and then only we can go for realization. But initially when we have to go for designing the filter, the step number 1 is we have to find the HD of e power j omega. So in case of low pass filter, the HD of e power j omega, you can see here all the characteristics are given here. The low pass filter, according to the definition, it passes only the lower frequency components and block the higher frequency components. So it passes the frequencies up to its cutoff frequency, which is denoted here by omega c. We have written the other side also, because when we are going to design the problem, on that time we have to take the range of frequencies from minus pi to pi. So we have written the other negative frequency also, but there is no negative frequency exist in reality, but we have written here for design purpose, because the ideal range we have written here from minus pi to pi. In case of FIR filter, we have written omega lies in the range from minus pi to pi. So we have shown both the side of the response. So this is the low pass filter. You can see that the difference between ideal and linear phase filter is, in case of ideal filter we have not written the phase here. The phase of the filter is not written here, whereas in case of linear phase filter the phase is along with the magnitude is written in the given expression. So in case of this ideal filter, that low pass filter, this ht of e power j omega, its value is equal to 1. Its value is equal to 1 when the frequency lies in the range from where to where? From minus omega c to omega c. That is only written here. From minus omega c to omega c, the value of this ht of omega is equal to 1. And 0, its value is equal to 0 otherwise. That means other than this frequency range, the frequency response of low pass filter is considered as 0. When we are writing the same thing for linear phase filter, we are not only considering this magnitude, we are along with the magnitude we are considering here the phase also. We are considering the phase also. So this is from omega c to omega c. This is our ht of e power j omega. This is magnitude is 1 and its phase is e power minus j omega alpha, which is written here. In this range, the frequency range, the value is this and 0 otherwise. Similarly, the high pass filter, band pass filter, band stop or band rejection filter, frequency response is also written. So here in case of high pass filter, you can see that the filter passes the frequencies from omega c to pi, and it blocks the lower frequency components, which is written here. So within only this duration from here to here as well as from here to here, the value I have written here, you can see that the frequency range in two ranges, its value is equal to 1. So that is only written here. Other than that ranges of values of frequency, the value of this ht of e power j omega is 0. So similarly, same thing we have written here, we have only included the phase in case of linear phase filter. Now coming to the band pass filter, it passes a band of frequencies. Now you can see that both look similar but not same. In case of band pass, high pass filter, the range of frequencies from omega c to pi, but here it is a band of frequencies it passes, and from omega c to 2 pi the frequencies are blocked. So a band of frequencies are passed through this filter. So we have the range of frequencies for this band pass filter in this way, which is denoted here. Similarly, coming to the band stop filter, the response is completely opposite of band pass. So if we know the band pass filter, we can just write the complement of band pass filter response to get the band stop filter response, which is shown here. Now you can see that the range of frequencies 1, 2 and 3. We have here 3 range of frequencies where its value is equal to 1. And other than these ranges, the value equal to 0. Again, similar way we have written the linear phase filter. We have included only the phase of the filter. Remaining all other things are same. Instead of this 1, we have taken 1, but along with that the phase component is also considered in linear phase filter. We have seen the various frequency response for ideal filter as well as for linear phase filter. So in the design steps, we have seen that once we find out the inverse discrete time Fourier transform of ht of e power j omega, we are getting the response HD of n in time domain. That is the desired response in time domain, but it is of infinite duration. So how to make it of finite duration? By multiplying with window. So what are the window and window functions? That is listed here in this table. So we are going to use here rectangular window, Hamming window, Hanning window and Blackman window. Apart from this, we have some more other windows also, like Kaiser window and all, but we are going to use these 4 windows for designing the FIR filter using window method. So in case of rectangular window, you can see that here I have written the types of window. Here we have written, we have written both the type, like ideal filter or linear phase, because we do not know the specification will be asked in which manner, in terms of ideal or in terms of designing the linear phase filter. But ultimately we will be designing the linear phase filter, but if the specification given for linear filter, we need to correctly specify the window function, because the ideal filter, the range of the values of n is nothing but the samples, number of samples, how many samples to be considered, it is in this range. So minus of n minus 1 by 2 to n minus 1 by 2, where capital N is nothing but the order of the filter. So here in case of linear phase filter, the window function, the n value, the number of samples to be considered, how many samples of impulse response to be considered, is from 0 to n minus 1. Okay, so here in case of rectangular window, that is the simplest window type. Why? Because very simple, the window WR of n, which is equal to 1 in this range. So within this range, that means this function, it is equal to 1 in this range. The range is this. If I consider this as WR of n and this is n, if this is 0 and this is n minus 1 by 2 and this is n minus 1 by 2, this value is equal to 1 in this range. So other than this range, the value of this window function is 0. So obviously when we take this function and we multiply it with the infinite duration sequence HD of n, the multiplication result only from minus n minus 1 by 2 to n minus 1 by 2 retains, and the remaining thing becomes 0. So the infinite duration sequence is converted to finite duration sequence. And in case of linear phase, again same thing only. Here the window function will be from 0 to, now this is from 0 to n minus 1. 0 to n minus 1. This is n. If this is WR of n, its value is equal to 1 from 0 to n minus 1. Only the range of the samples from 0 to n minus 1, 0 to n minus 1 also n number of samples, and if we consider from n minus 1 by 2 to n minus 1 by 2, that also gives n number of samples. The number of samples we are not going to change, only we are going to change the range of frequencies. So this is the simplest window, the rectangular window. Coming to the next window, which is Hamming window, the window function is given in this manner, where this HM is nothing but Hamming, the notation for this Hamming window. This equal to 0.54 plus 0.46 cos 2 pi n divided by n minus 1. This is for ideal filter. If the filter is linear phase, there is no change in the equation except this sign. So instead of that plus symbol, that is changed to minus. So we can easily remember this window functions. This window functions will not be supplied if any design is asked in the examination. Only we have to remember, because it's very simple to remember. Even you can remember using a technique that this 2, if you add, the answer is equal to 1. In that way also you can remember. Next is Hanning window. So Hanning window, it is specified, it's much more simpler than Hamming, because here we need to remember these two things. Here it is both 0.5 and same thing, same. If you remember this Hamming window, Hanning is similar, only this, instead of this 0.54 and 0.46, this both become 0.5. Again I said that this ideal and linear phase, only here the sign is differing, remaining things are constant. Here in this case, in case of Blackman window, you see that we have 3 terms instead of 2 terms here in the window function. So it is 0.42 plus 0.5 cos 2 pi n divided by n minus 1 plus 0.08 cos 4 pi n divided by n minus 1. Whereas in case of the linear phase, we have only this first symbol is changed from plus to minus, the second one no change. So we have to remember these window functions when we are going for designing a FIR filter using window. So step number 1 is first specification given, will be drawing HD of e power j omega. So we can find out it is low pass, high pass, band pass or band stop. Next thing is we'll be taking the inverse discrete time Fourier transform, will be getting HD of n. That HD of n we will make it finite by multiplying with any one of window function based on the specification. Then it will become finite range. Once we find out h of n, which is nothing but HD of n into this window function, then we can go for writing the transfer function h of z, and then once h of z is written, we will be realizing the filter.
So far we have seen the design of IIR filter using impulse invariant and bilinear transformation, but both the transformation has its own pros and cons. So we'll discuss one by one. So first I'll discuss about the impulse invariant transformation. So in impulse invariant transformation, the relation between the frequency is omega is equivalent to omega t. So this leads to the linear response. So when we plot the omega versus omega, so when I consider the sampling time period is equivalent to 1 second, it leads to the linear response. This is the advantage of the impulse invariant transformation. Now the other side is its disadvantages, that it has the aliasing effect. So the aliasing effect can be explained in a better way with the help of the conformal mapping between the S-plane and Z-plane. So we already know the poles which lie in the imaginary axis of the S-plane will be mapped into the on the axis of the unit circle of the Z-plane, and the poles which lie in the left hand side of the S-plane will be mapped interior circle of the unit circle, and the poles which lie in the right hand side of the S-plane will be mapped outside the unit circle. So this is a conformal mapping between the S-plane and the Z-plane. So all the frequencies, all the digital frequencies in the range minus pi to pi are unique. The analog frequencies in the range minus pi by 2t to pi by t will be mapped in the range of minus pi to pi. But the other side, when the poles are lying in the range of pi by t to 3 pi by t, this will also be mapped in the same range of minus pi to pi. That is, in the interval pi by t to 3 pi by t, and also the other side minus pi by t to 3 pi by t also lies in the same region minus pi to pi. For an example, let us consider a pole Z1 and the S1. So the relation between the Z1 and S1 is Z1 is equivalent to e power S1 into t, and the pole in the Z plane can be represented as sigma plus j omega. So S1 is equivalent to sigma 1 plus j omega 1. I'll consider another pole also, Z2 and the S2 relation. So Z2 is equivalent to e power S2 into t. So I'll consider the pole S2 as sigma 2 plus j omega 2 plus 2 pi by t. That is, I'll consider the pole lying in this region. This region is called as the overlay region. So now, when I expand this, Z2 is equivalent to e power, I'll substitute the S2 value, sigma 2 plus j omega 2 plus 2 pi by t into t. So this is sigma e power sigma 2 plus j omega 2, and this t gets cancelled, so it becomes as e power 2 pi, into 2 pi. So this value is equivalent to 1. So again Z2 will be equivalent to e power sigma 2 plus j omega 2. So again this pole and this pole Z1 lies in the same point. So this is called as the aliasing effect, and we term it as many to one mapping. So this is a drawback of the impulse invariant transformation, but this problem does not arises in the bilinear transformation. So the advantage of the bilinear transformation is it has one-to-one mapping. But the drawback of the bilinear transformation is the warping effect. That is, the non-linear relationship between the analog frequency and the digital frequency, and it is given by the relation omega is equivalent to 2 by t tan of omega by 2. So this leads to the non-linear response. So when we do a analysis in the impulse invariant transformation, omega is equivalent to omega t, so it is said to be a linear response. But when we come for the bilinear transformation, this omega is equivalent to, so just when we cross multiply it, 2 tan inverse of omega t by 2. So this is said to be like a non-linear response, and this is a drawback of the bilinear transformation. So now a short description about both the transformation. The advantage of the impulse invariant transformation is the linear response, that is the relation between the analog frequency and the digital frequency is linear, but the drawback of the impulse invariant transformation is the aliasing effect, that is many to one mapping. The advantage of the bilinear transformation is one-to-one mapping, but the drawback is the non-linear response, that is the non-linear relationship between the digital frequency and the analog frequency. Thank you.
Already we have seen the design steps for FIR filter design using window method. Now we will be designing one FIR filter based on the given specification. So already we have seen the steps related to filter design, where ht of e power j omega, the magnitude response or frequency response, how to define for various filters. Then we have seen various window functions. Now we will be implementing those steps and we will be designing the filter. So let us take one example. Here we are taking one example of designing an FIR filter, where it is given as design a FIR filter which passes the frequencies above pi by 2 radians per second, and also it is given that use Hamming window. Now how we are going to design the FIR filter? So according to the design steps, the first step was to draw the desired frequency response. Now from the given specification, the filter passes only the frequencies above pi by 2 radians. So if we draw it graphically, so here that can be represented in this way, where this is the high pass filter. So directly if it is given high pass filter, we can take, or from the given specification also we can find out that the filter, the given filter is high pass filter which passes the frequencies above pi by 2 radians up to pi. So we are writing both the side, because we will be designing, nothing mentioned, it is linear phase FIR filter or ideal filter. So first we will be designing one ideal filter, and then we will be converting that ideal filter into linear phase. So according to the specification, it is given here, the filter specification passes the frequencies above pi by 2 and it will be up to pi, because we are considering the range of frequencies from minus pi to pi. Now this amplitude is 1 here. So here this is given omega c is pi by 2. Now what is the second step? First step is, so we know that the steps are, first is we have to draw or we have to write the desired frequency response. Second step is we have to find hd of n, and third step is we have to find h of n. Fourth step is we have to find h of z, etc. So here this we will be getting by taking the inverse discrete time Fourier transform of hd of e power j omega. So what is, this is our step number 1. If we mention this is our step number 1 we have drawn. Second step is, in the given equation if we substitute the upper and lower limit, we will be getting the expression of hd of n is 1 by 2 pi. The upper limit is that is the variation from minus pi to minus omega c. So here the upper limit is minus omega c, then minus pi. For the second integration, the upper limit is pi and this lower limit is omega c. Now if we solve this, so what we can do, we can combine these two terms together and the remaining two terms together, so that we can write in terms of sine or cos formula. So here we can bring that jn outside. So we will be getting e power j pi n. I can write in this way, just rearranging the order. j pi n, this is 1, plus the other term is, I am taking minus as common from this both. Why? Because I want to write the positive term first, that is e power j omega c n. Then I am writing that as minus of e power minus j omega c n. Why this was plus? Before that I have already taken this minus as common, so minus of minus become plus. This term is already minus. Now you can see that why I have written in this way. There is a purpose. The purpose is I can simplify this in terms of sine or cos, because outside we have already this 2 pi j n. So what we can bring that, we know that e power j theta can be written as cos theta plus j sin theta, and e power minus j theta can be written as cos theta minus j sin theta. So if we try to combine this here, if we write e power j theta plus e power minus j theta, if we add this both, we will be getting 2 cos theta, or it is cos theta equal to e power j theta plus e power minus j theta by 2. So here similarly we can write sin theta as e power j theta minus e power minus j theta divided by 2j. So you can see that if I am able to bring here one 2j, I can write that in terms of sin theta. So what I am doing here, this 2 and j, I will be taking it inside. So I have here pi n, and this can be written as e power j pi n minus e power minus j pi n divided by 2j, minus this term is j omega c n minus e power minus j omega c n divided by 2j. So this can be written as sin pi n, whereas this can be written as sin omega c n. We know already the value of omega c. Omega c is equal to pi by 2. If we want, we can substitute the value initially, or at last also we can substitute. So or we can write this as 1 by 2 pi n by substituting the value of omega c equal to pi by 2. This becomes sine of pi n minus sine of pi by 2n. So let us give this expression number as 1. Now what we received is hd of n. What is this hd of n? Is the desired filter's impulse response. Now this impulse response hd of n, it is of infinite duration. So what is the duration of this? This is from minus infinity to plus infinity. So this will not give the FIR filter. So what is the next step? Step number 2. So this is over, step number 1 over, step number 2 over. What is the step number 3? So in step number 3, now we have to find out h of n, which is of finite duration, by multiplying this hd of n with the window function. So already we know the window function, already specified. I have given the table also. We will be taking the values from the table and we will be considering this hd of n, same hd of n, w of n, which is for Hamming window we have to consider that function. Both will be multiplying and we will be finding the value of h of n. Now you see that this hd of n, it is from minus infinity to plus infinity, of infinite duration. Here in the given filter design, let nothing given here. So let us consider, let n equal to 9. Suppose we are considering n equal to 9. Now we need not find out all the infinite values, because that will be waste of time. So we can consider the values, only the 9 samples of hd of n. This hd of n, what we have computed here, is of infinite duration, from minus infinity to plus infinity. Now when we are going for FIR filter design, which is of finite duration length, that h of n will be of finite duration. So we need not consider or find out the values of hd of n for infinite sequence from minus infinity to plus infinity. Only for the specified order of the filter we can go for finding the value of that many hd of n samples. So let us consider, we need to design a filter of order n equal to 9. So let us consider n value equal to 9. We are going to find out now 9 samples of the filter. So this hd of n, what we are going to consider, should be of length minus of n minus 1 by 2 to n minus 1 by 2. Why? Because we are considering the filter as ideal filter. Now what is given? N equal to 9. So what is 9 minus 1 by 2? So we are considering let n equal to 9. Then in this case Hd of n we can consider from minus n minus 1 by 2 to n minus 1 by 2. We need not consider all the samples of Hd of n. So if n equal to 9, this becomes 9 minus 1 by 2. So from minus 4 to 4. So if you consider the samples in this range, that itself enough. Otherwise we'll be simply computing all the values and then later we'll be neglecting all the values when we are multiplying with W of n, because this W of n for ideal filter for n equal to 9 will be specifying for this range alone. So what we are doing here, for Hd of n also we are going to find out the value from Hd of minus 4, then Hd of minus 3, Hd of minus 2, Hd of minus 1, Hd of 0, etc. and then it is 2, Hd of 3 and Hd of 4. So this many samples first we'll be finding out. Once we find these samples using the expression what we got, the expression number 1 Hd of n, by substituting the value in the expression what we got Hd of n is equal to 1 by pi n sin pi n minus sin pi by 2n. In this expression if we substitute the value for n, we will be getting the values of Hd of n. Now when we will be finding the values at one condition, we will not be getting the values as it is, we will be getting a condition where we will get 0 by 0. So when we try to substitute the value of n from minus 4 to 4 in this formula what we have already derived, we will be getting the values of Hd of minus 4 to Hd of 4. So directly by substituting the values of n in calculator in normal mode, we can get the values except this value. Why? Because here when we substitute the n value equal to 0, in the numerator as well as in the denominator we are getting 0. So when it is 0 by 0, it has become undefined and will be not be able to find the values of this Hd of 0. So how to find this Hd of 0? For that we will be applying the rule which is called as L'Hospital rule. According to this L'Hospital rule, when we are getting any function of 0 by 0 form, if we are applying the limit, now this can be written as this Hd of 0 can be written as limit n tends to 0. The numerator is sin pi x, denominator also pi x. So if both are same, limit n tends to 0, sin pi x by pi x can be given as 1, can be written as 1. Similarly for the other term, if we write that is minus limit n tends to 0, I have sin pi n by 2, down also I must have pi n by 2, but I have only pi n. So what can be done here? We can compensate the 2 by multiplying 2 in the denominator. So you can see that this whole term will be giving me 1. So this is 1 and down I have one more 2. So 1 minus 1 by 2 is nothing but 1 by 2, or which is equal to 0.5. So we are getting the values of this Hd of 0 as 0.5. So we have computed the values of Hd of n from minus 4 to 4. Why minus 4 to 4? Because we are going for designing the ideal filter first. In the specification it was not mentioned the filter is linear phase or ideal. So we have started with ideal filter design, later we will be converting it. Next, so we have found out Hd of n within that range from minus 4 to 4. Now we will be considering the window function. So the window function to be considered, it is given as Hamming window. As we know, the Hamming window function for ideal filter is given by this expression. Now we can substitute the value of n from minus of n minus 1 by 2 to n minus 1 by 2, that is from minus 4 to 4, because in this case our capital N is equal to 9. So we will be able to find the value of window function from minus 4 to 4. So these values are calculated using this expression by keeping the calculator mode in radian. So if we keep the calculator mode in normal mode and if we try to calculate the values will not be correct. So we have to set the calculator mode to radian, and then by substituting the value of n from -4 to 4 we will be finding the values of window function. Now what is the next step? Next step is the window function to be multiplied with desired impulse response to get the actual response of the filter. So when we multiply this ht of n with the window function, so what is this h of n when n equal to -4? So this just by substituting n value from -4 to 4. So first value I have taken n equal to -4. This is ht of -4 multiplied by whm of -4. Both the values already we have calculated previously. So we will be taking, and then if we multiply we are getting the result for actual response. So the actual response is now calculated from h of -4 to 4. So here if we try to plot this actual response, we can see that it is from -4 to 4. The values are plotted here. Now you can see that this filter, when we try to write the transfer function h of z by taking the z transform of this h of n, we will be getting here, because of the starting point of this actual response is -4. So what is the z transform? We know the z transform formula is from, in this case it is from -4 to 4 h of n into z power -n. So if we try to substitute the value here, some of the values will be getting as z power 4, z power 3, z power 2, z power 1, etc. So to realize this kind of filter, we do not have the components, because we cannot implement the filter in terms of z power 4, z power 3, etc. We need the delay elements. So this filter what we are getting here is not physically realizable filter. So to make the filter as physically realizable, what we need to do is we need to multiply this h of z by n minus 1 by z power n minus 1 by 2. So we will be doing it later. Before that, let me find this h of z. So according to this, when we substitute h of -4 z power 4 plus h of -3 z power 3 plus etc., we will be getting the values. The last value will be h of 4 z power -4. So once we find out the values, we can see that these terms cannot be realized in practice. So what we need to do, we need to multiply this h of z. This h of z should be multiplied with the z power minus of n minus 1 by 2. So what is our n here? N equal to 9. So 9 minus 1 by 2, that is z power -4. So this h of z should be multiplied by z power -4. So let us give this expression as 2, and now this expression is 3. So what we will be getting as h dash of z, which is physically realizable filter, that is h dash of z will be h of -4. Already we know the value of h of -4 here. H of -4 multiplied by z power 4 into z power -4. So z power 4 into z power -4, z power 0, plus the next term is h of -3, z power 3 and z power -4. It is become z power -1 plus h of -2, z power -2 plus h of -1, z power -3 plus h of 0, z power -4 plus h of 1, z power -5 plus last we will be getting the term h of 4, z power -9. So you can see that this filter is physically realizable filter. That means we have designed a filter which is physically realizable. Initially we started with ideal filter design, but since the ideal filter cannot be realized in practice, so we have multiplied this ideal filter transfer function h of z by z power minus of n minus 1 by 2, so that the ideal filter is now converted to linear phase filter, which can be practically realized by using the adder, multipliers, delay elements, etc. So already we have found out this h dash of z, which is physically realizable filter transfer function. Now by substituting the value of h of -4 to h of 4, what already we have calculated, in this expression we will be getting this h dash of z. This h dash of z is the transfer function of physically realizable filter. This filter can be realized in practice. Why? Because to implement this filter, the components required are this two terms are multiplied here, so we need multiplier. Then this z power -1, z power -3, z power -4, all these are the delay element. So we can consider the delay elements multiplier as well as this summing operation or summer or adder can be used for implementing this filter. So we have completed the FIR filter design, high pass filter design, linear phase FIR high pass filter design, and we have got this h dash of z. This h dash of z can be implemented easily using the components, filter components.